So in the companion video to this, in part one, we looked at energy balances a little bit in control mass problems. And we were focused specifically on path functions versus point functions. So we're doing that in the context of this practice problem where we're looking at the change from 300 kilopascal and 250 C to twice the initial volume and a final pressure of 400 kilopascal. So we're going to be looking at three different processes where we're changing from this initial state here to this final state here. Going about it by three different pathways. This first pathway that we looked at in the last video, we're looking at first a constant pressure process, then a constant volume process. So if we flip to the next part, we're going to look at two different ways that we could go from this initial state to this final state. Lots and lots of different ways. These are just two. So we're looking at in part two, we're looking at now constant volume first. So this first is constant volume, then a constant pressure. So the first time we did it, we looked at constant pressure, then constant volume. Now we're going to switch those. So we're going to start with the same initial state. I already wrote some of this down. And we're going to the same final state. So we know where we're going to end up. 1.593 for our volume. Maybe we remember that from last time. And our final value for internal energy, which we looked up last time, is 4273 kilojoules per kilogram. We can look up both our volume and internal energy for this center state, state 2. So the volume, we know it's the same as the initial volume because that first step is constant volume. So this is 0.7964 meters cubed per kilogram. And once we have that volume, we can look up internal energy. All right, so we find work in this for both of these pathways. So from 1 to 2, we find the work, then we find the work from 2 to 3. In both of these, we're using the same integral, the integral from 1 to 2 of P d capital volume. For this first step, we don't have a change in volume. So we have 0, right? And I'm going to write no volume change. Then for 2 to 3, we're going to look at the integral from state 2 to state 3 of PdV. Right, this one, P comes out of the integral because it's a constant. So this is simply equal to pressure delta volume, which is which is 400 kPa from state 2 to 3. So here in state 2 to 3, we're now at 400 kPa times 0.10 kilograms times the change in volume, 1.593, 0.7964 meter cube per kilogram. So we see a work of 31.86 kilojoules. If we graph that, we first have if we graph that here, we first from 1 to 2 have a constant volume process. Then from 2 to 3, we have a constant pressure process. As before, the work is the area under the curve here. So this is work. And the reason that that first step between 1 and 2 has 0 work, right, is because there's no volume change. There's no movement in the boundary of the system, so we don't have any work. On this graph, it's a vertical line, so there is no area under that. There only is under that second part. All right, now let's do one more step. Now we're going to imagine we are expanding, say, against a spring. So there's going to be a linear change between pressure and volume. We're still going to get from the same initial state to the same final state. Our system is going to look really similar. We're still going to try to solve the same integral. So how would we solve this integral here? Well, one way that we could do it, we could get how pressure and volume are going to change together. So if we're going to have a linear change, say between here at 300 and there at 400, we're going to have a linear change in volume and a linear change in pressure. We could get an equation for how pressure and volume are related. So we could substitute in an equation something like this. So pressure equals 300 plus 100 V minus 0.7964 divided by 1.593 minus 0.7964. So that's simply the equation of the line that I have drawn there. Maybe it looks a little bit like the equations that we used for linear interpolation, because it exactly is. We could plug in P as a function of V. So we plug in this equation, then we can integrate using the same kind of integration methods that we would use in a calculus class. That's one way to do it. Another way to do this would be to solve graphically. We should get the same answer. So the area under this curve should be work. So we can just look at that and say, what is the area under that curve? Let's do some basic geometry. This is going to be equal to mass times little w, 1, 2, which is 0.10 kilograms. That's our mass, times the area under the curve. So that's going to be the midpoint here times the change in volume. So 300, 350 kPa time, that's that center point right there, times the width. So the width of that shape is 1.593 minus 0.7964 meters cubed per kilogram. And this would give us the same answer as the more complicated integral that we would do before, and it would be 27.87 kilojoules. So 3 different pathways, 3 different works. We're going, just to reiterate, we're going from the same initial state, the same initial internal energy, to the same final state, but we go from about 28 kilojoules, almost 32 kilojoules here in this case, and our very first problem we were about 24 kilojoules. Path matters for work. So just to go back to a system that's a little bit like a problem that maybe we would have solved earlier in the class. These problems are going to work a lot like they have previously. We're just going to have a slight tweak on how we do the energy balance. So we can apply the second law like we've done before in the past, where we have things like adiabatic reversible processes, for example. if we look at this particular adiabatic reversible process, say we have an expansion from 500 kPa and 350 C down to a final pressure of 100 kPa. If we know that this is adiabatic and reversible, we know that delta S is equal to 0, just like it has been in the past. We can look up that initial state. So this is an internal energy of 3128 kilojoules per kilogram. And we can look up the entropy, 8.087 kilojoules per kilogram Kelvin. Now, if delta S equals 0, then we know S2 is equal to S1. And we know what that is because we just looked it up. 8 kilojoules per kilogram Kelvin. This can allow us to look up the other properties that might be of interest, like say U2, which is 2756 kilojoules per kilogram. We could also look up something like T2. We might not need to, but just for example, this would be about 154 Celsius. Okay, so similar to how problems that we've solved before, we have this adiabatic reversible expansion. We go from high pressure, high temperature down to low pressure and low temperature. This we could solve directly for work, something like this. W12 equals the integral of P delta V. But we can only do this if we know how pressure, sorry, not P delta V, P dV. We only can do this if we know how pressure and volume are connected. So this might be possible. We'll look at this eventually, but a simpler way is to look back at our energy balance like what we've done before. So we have something like delta U equals Q12 minus W12. Q is equal to 0 because we know it's adiabatic. And then we can write down delta U out minus in, 2756 minus 3128 kilojoules per kilogram equals minus W12. So W12 is 372 kilojoules per kilogram. Okay, so this would be for our ideal system. We could repeat this now if our process is, say, 75% efficient. So our first step would be solve the 100% efficient case. We've just done this. W12 ideal was 372 kilojoules per kilogram. Step 2 would be like it has been before, use efficiency. So W12 real is 0.75, we're 75% efficient, times 372 kilojoules per kilogram. So this is W12 real is 279 kilojoules per kilogram. Okay, 75% of the ideal value because we're 75% efficient. And this is a work generating process. Remember, if it's a work consuming process, that gets flipped and we would have divided by 0.75. Now we could do an energy balance. Again, so that would look something like this. Delta U equals Q minus W. So we could use this to calculate the final U2 real minus U1 equals minus W12 real to calculate that final internal energy if we needed that for some reason. So again, really similar to what we've looked at before. A lot of these are going to be similar. We'll get some practice. Sometimes a little tricky to know when we're going to need to do, say, something like this, where we calculate work directly, versus something like this, where we use an energy balance to calculate work. The short answer is they both are correct. We can do either of these. This is generating, or this is calculating work for ideal systems already, delta S equals 0 systems. So both of those would have been effective ways, but the challenge is whether we know how pressure and volume are related. Some systems we do, some systems we will really closely, and we'll cover that actually fairly soon. But that's all for this video, just to show some basics of how we can do some control mass problems, how path functions work, and how we can apply the second law similar to what we've done in the past.